자, 여기가 지금 참석한 학생 리스트입니다. 오케이, confirm. Now, 오늘 수업은 아주 짧게 진행을 할 겁니다. Let's say we're gonna have a very short class today, only about 30 minutes. And I would like to mainly discuss and explain how to use 3D beam for explaining a little more advanced feature. 오늘은
교수님 이렇게 하는 겁니다. 3시간 내지금 해야 됩니다.
자, 그 마이크로폰을 좀 꺼줘요. 자, 그래서 as I said, today class will be very short, about the 30 minutes. I will mainly like to emphasize how you can do better job for yesterday's task. 어저께 그까지 제출을 해야 될 그 타스크 있었죠? 타스크에 대해서 좀 더 advanced 된 방법을 제시해 줄 거예요. Today I'm gonna discuss a little more advanced method. 누가 이게 자꾸 이게 네, 학생들 앞에 이거 쓰고 그러지 마세요. Okay, so we had some homework, and so we had a homework which was due yesterday, but today I would like to spend about only 30 minutes to explaining how to increase the how to better design the cross section, especially the airfoil. Okay, that's the main topics I would like to emphasize. And then each group will work together one more time to better design. 아이 참네, 소리 좀 꺼달래니까. Okay, so I distribute two files. One is this manual for 3D beam, which I sent you several days ago, and I also send you the a 3D beam, which is the same as you have, but I have added some sample case. 지난 며칠 전에 내가 이 그 3D 빔 매뉴얼과 이 3D 빔 파일을 다시 보냈죠. 뭐 새로운 건 아닌데 it has 내가 새롭게 보여줄 내용이 추가되어 있어요. 뭐 없어도 여러분들이 지금 추가하면 됩니다. 그래서 중요한 포인트는 여러분들이 뭐 처음에 이 내용을 보면은 introduce the 3D beam starting with material, laminate, and section, and global geometry and load and solve. Well, you already know all these procedures. There are some other functions which are new to you. Then you don't have to try to understand, such as a high fatigue or other function. That is for the advanced users. All you need to know is the just these several steps. And there is a section, briefly, section for the 3D beam theory. And there are a lot of mathematics involved here, but I just want to share with you how this, what kind of theory was used to develop this tool. Briefly speaking, we have a displacement and we have a strain displacement relations, and we have a module how to calculate the section property, such as a bending moment of inertia. And last one is the finite element formulations, which is very important formulation based on energy method, which is equivalent to force equilibrium. Okay, this is equivalent to a force equilibrium, but to solve this equilibrium equation, we cannot directly solve the equilibrium equations. Instead, we need to use energy method, which we will cover in last chapter of this semester. So anyhow, all we go through all these chapters. Finally, we have a governing equations. For static case, we have a stiffness matrix K, and this is a D displacement, and this is the external force. I don't mean to discuss too much about the theory, but I like you to just remember that this 3D beam is based on finite element formulations. And there are several other slides explaining more about the coordinate system, and which you don't need it. You don't need. This is mainly for advanced user, such as a design of the composite, which has the certain fiber direction. So for the isotropic material, which we are studying now, we don't need this coordinate system. So let me skip that. And there is a several couple of slides explaining all the worksheet. There's a worksheet, material DB, and worksheet, laminate, and worksheet section DB. We already know how important they are. You start with the material DB and laminate and section, and there is a geometry and load. And all these, once you enter all information, and then we go, this program will give us the KD equal F, and then we solve this one, we get the displacement D, and then strain and stress and failure index. Okay, keep in mind that try to compare the procedure we already learned in the class. All the basic, the fundamental procedures, you know, the 3+, 5+1, 8+1 flow procedures, very similar to that one. And then there are another slide, more about this, explain the worksheet and explain the visual basic, but again, this is just a brief overview, and I hope you just get one idea about this one, not in detail. You don't need to understand not in detail, and the same thing. And one thing I really like to emphasize today is that how to model airfoil geometry. So this is an all material property again. You already know that you can define your own materials and be sure to have your own material name. Okay, it's a name, and you can enter stiffness and strength, and also density. You know, the gravity here, gravity is a 1 point whatever number. Still, in case of steel, it has a 7.5 and something like that. And laminate consists of several layers of material and thickness and angles, which we already know. And section, you can define many different sections. And speaking of the section, we can have a closed section, we can have an open section, we can have, for the closed, we can have a circular one, and you can have a rectangular, you can have a elliptic with several cells. This is called cell, each one called cell. So this is a one cell, and this is another cell, and so on. Now, importantly, how to generate airfoil. Airfoil cross-section is very critical, very important for, in the case of design of an airplane, in the case of design of a wind turbine blade, and so on. And open section, we don't have any cell, it's just open with the different shapes, angle, T-shape, I-shape, or channels, and so on. Now, the point is that others, such as the elliptic or rectangular or others, can be done without much difficulties, right? It's just a matter of practice. Now, today I would like to emphasize how to generate this airfoil. That's the one point. And this is just a brief introduction of modeling of this airfoil. Airfoil and the shape and then the layups can be modeled as this one shell and with a certain laminate. So even this procedure, to follow this procedure, you need to have all the coordinates, but we do not have much information of this airfoil. So won't be easy to generate all this airfoil. So there are very special a feature is called generation of airfoil. Airfoil, there are hundreds of different types of the airfoil. Airfoil is the profile for airplane wing, and as you can see, there are different types of airfoil, and one famous one is called NACA type. So wing airfoil NACA, and it followed by a 4-digit. There is a 4-digit number, and each one has this certain a meaning. So maximum chamber and chord length and MPT value. You can find more. You can find more information from internet. And also you can have a 5-digit. In case of a 5-digit, more in detail, more a little different. But we need to understand the terminology. What is a chord? What is a chamber line? What is the percentage? And so on. This is just a brief introduction of airfoil. And in 3D beam, all you need to do is to enter 1, 2, 3, 4, 4-digit. And then you will have this all airfoil. Now, as you know, this global geometry means that we need to generate a line out of this airfoil. But I like to emphasize how we change the airfoil shape along this beam. Okay, we need to change the airfoil. And how do we change the airfoil and how we apply the load? Load and boundary condition is very similar to a previous case, so it's not difficult at all. But here, the airfoil, generation of airfoil and how to change the shape of airfoil is the critical procedures. And it's also good to know how to generate Abacus info file. This is optional features for advanced user who want to model using the Abacus. Okay, so there are several sections for the verification. I will skip that. I would like to emphasize on the this one. You can just follow to make sure that you can regenerate. You can generate any circles like that. So it's no problem. I'm sure you can repeat very easily. And now, this is the one I'd like to emphasize. Use just manual 3D beam for wing analysis. Wing analysis, again, we need to generate these wing cross sections. And for this wing cross section, there is a web. Web is the connecting structures, top and bottom structures, and how we generate a wing, how we connect them. That's the one thing we need to understand. That's a major one I would like to cover. So there are certain numbers, and here I will go back, and it's easier to use this real Excel, and let's go to sorry, this is a go to a section. If you go to a section, there is a you can enter values, any worksheet, to generate a section. As you can see here, there is a option for airfoil. See, there was an option for circle or elliptic shape. You enter 1, right? And if we want to generate a line, you enter 0. And if we want to generate the airfoil, there is option 2. So you can start from this blank, or you can start from other worksheet called section airfoil. Okay. There is a section airfoil which you can modify. It's much easier to modify this one. Okay, I will like to explain what is that. Let's first change all the layouts. You don't have to change all the different layout. Let's say we have all the same laminate and steel. We have a laminate called steel, as you can hear. Do we? Oops. Yeah, this is a little different. We can create. You can have a steel, and you can have all 0. Okay. Be sure to have your own dB. Say you have a steel, or you can have a defined aluminum as you like the steel. So this is the material with the steel. Yeah, please be careful about this material name steel or laminate name steel. Okay, or you can have this one steel. Different name, but it is okay. So go back to this. Where is it? Airfoil here. So we use this steel. I just want to make sure that same, even the capitals. And number of division. What is the number of division, and what is the option 0? Well, as I mentioned, to generate the airfoil, we now need to enter number 2. Number 2 is the airfoil generation, right? Airfoil generation. So what we like to do is certain airfoil with this cross section. Okay, this is what we like to do, and then I would like to introduce. So first line is the enter 2 here, and number of division 5 is and what is the option 1? Okay, in case of 2, now we have a division is 5. Now, in case of 2, there is a key point number key point number for the center. So only key point number, this is only one center. So that you enter. Now the next one, option 2, is a user airfoil, which is the important number. So if I click that, user airfoil, you can define own airfoil, but it's difficult for you. So let's say if the number is the bigger than 999, that will be a NACA. You can call it NACA, NACA number. So 2422. 2422 is a NACA number, and there is another worksheet. I will show you. This is the NACA worksheet, which will automatically generate a wing profile. I mean, you don't have to look at it, you don't have to fully understand, but just if you are curious, if you 2244, you can see that the geometry is automatically change that. So if you know how this number means, you know, this again, there's a 4 numbers, 2240. So 2240 is the maximum camber and relative and so on. And this is all the Excel, which will automatically generate the wing shape, profile, NACA. And this all generate the number, as you can see, if I click this one, and this is the one, okay, I will show you again. This one is automatically this, as you can see, all the equations, okay, all the equations, and 2240, and change this shape. And this shape will be automatically transferred to this section, okay, the section we just enter. So 2422 is the one we are choosing from the NACA. Now, what is the zero? Next one is the XPG and encode. And what is the XPG and encode? And this one, this code is the 2. What does it mean 2? 2 is the code length. This is the 2 meters. See, all the shapes which will generate from NACA is all normalized. What does it mean normalized? All the airfoil has the a unit length. Unit length means that it's a non-dimensional value. It's not easy to see, but the but anyhow, you can see that there is a 1.0. So all airfoil has the I'd like to increase. Okay. So this is a 1.0. So all airfoil shape is just represent from 0 to 1. So this is just a shape. If you want to give a real dimensions or length, such as you want to generate a 2 meter, you just enter 2. Okay, this is a 2 meter. This is called code length. And X pitches is that if you have this is a y-axis and this is a z-axis, and X pitches is that where does it start, this point. So you can just start from 0. There's no problem. And next one is the either 1 or 2. There is a option for the 1 or 2. So if we want to generate, this is a top skin, usually called suction side or pressure side, but I'm going to use the top skin. If we want to generate this top skin, you can just call 1, okay? And if bottom is, it can be 2. Actually, before, okay, so this is the top skin, and what is initial and last? Initial and last means whenever we want to add some other divisions from this part, you could have a different laminate, and here you could have a different laminate. So you have a 1, 2, 3, and 4, 5, 6, 7, and 8. Okay, so you have a 1, 2, 3, 4, 7, and 8 different laminate. So so X point is starting. I'm sorry. Initial X is a starting. This is all 0 to 1. Okay, 0 to 1. So starting from 0 and until 0.3, this is the 0.3, and the top is this part. So this part has a number of division. You want 5. And next one is exactly same. Exactly same. You just copy and paste, and then you can have a 0.3. This is a 0.3, right? 0.3, and then here you have a 0.6. 0.6. So from here to there, you can generate this line. You have a number of division 5, and you can have a still laminate. And the third one, we start from 0.6 to 1. Again, this is a 1 and 0.6. This is a top. We can call trailing edges. And others number is exactly the same. And you can repeat. You can repeat these procedures for the bottom one. Okay, bottom one. You just repeat bottom one, and then same divisions, but only difference will be this 2 to 2, means that the bottom, okay, this bottom surface. And then we want to generate this shear web and this shear web. So first shear web, you to generate the shear web, there is another option for the 4. So okay, those is called web. Okay, web. And so these are 4, and starting point and same and same, all same, but here is a 0.3 and here is a 0.3. That means that here, as you can see, that X at the upper skin, X at the lower skin. So you can see that this shear web, you have a top 0.3 and bottom also 0.3. So 0.3, 0.3, you connect them. Okay, and second web is a 0.6, 0.6, you connect them. Okay, and so this will complete a airfoil which has the 2422. And let's see how it generates the sections airfoil very easily. You all you need to do is just select this airfoil number, NACA number, and how many times, I mean how many number division, and then you select certain a position of these each sectors, and it quickly show you all the shapes. Okay, this is the one we just generated. Okay, this is the one we generated. Don't look at the lengthwise. This is the one we just generated. Okay, and now the rest of them we have a long cross section has changed. I will how to change the cross section? Well, there is another very important number which I didn't explain, was this one. Okay, let's say I will try this 1 and 1, and I will just do, and then I will just do this. Okay, I will explain. There is a scale, initial, scale factor, initial and final, and as initial and final. So whenever we have a section, we have a coordinate. This is the y, and this is the coordinate and z, right? And then this one will have a x-axis. X-axis goes this way, and we want to change this scale. So along x, and there will be initial. Okay, y initial means the y initial. Initial is the configuration we enter here, and z scale initial is also 1 here, and y and z. Now a y final, this is a final scale, is a 1. 1 means that at the very final will be scaled all equal 1, means all same. But if we want to change something like a 0.5, and also we want to change in the z direction, in scale factor is a 0.5. So 50% reduction at the end. Okay. So how many this one will generate a certain number of section, 1, 2, and 3, and so on. How many? A number of 10. So this is a number of 10, and this is all the scale factors, and this is an angle. Sometimes we want to generate angle here, there, and there. We want to generate angle rotations, which is starting from a 0 to final. But if we don't want to use it, just enter 0, 0. Okay, and so now this is the x location and initial and final, and this x is the 10, means that this is just for showing the geometry. All these lengths will be defined in geometry. So this one is generated just as sections. So this has no meaning. So don't need to pay much attention to this 10. This is again just to show the cross section. So let me, to have a constant, you just enter all 1, and then this, you don't have to make many sections because they are all same. So enter 1, and then you will see this is just one a airfoil without any scale, only one database, and this will show you a constant, just one database. Okay, just one database, and this is the one we just generated. Okay. As you can see, if we want a little more smooth, see here, if you want to see the number here, and here from this is the corner, and this is the remember this is a 30% and 60%, and this is 100%. This is a typical way of generating airfoil. Now from here to there is we specify 2 meters. So it shows all 2 meters dimensions, okay, and also the bottom one. See here, how many laminate do you have? 1, 2, 3, 4, 5, and also 1, 2, 3, 4, 5. Why 5? Well, because we specified 5 here. Now I'm going to delete this one. See, we have a 5 here. So if we want to change this one as the 10, no problem. And if we want to change the here is a 10, then these leading edges of this part will have a more smooth curve, right? Smooth curve. Let's see how it change. So this is the important feature of the 3D beam to generate an airfoil, and for your further study. Okay, now you can see that very smooth curve, right? More smooth curve. You can see that. Okay, that's the number of division. You can generate more. Now, if we want to get rid of web, say, I don't want to generate this web. Let me save as. Okay, I don't want to I want to save this one somewhere. Okay, and then I just want to delete these values. Okay, now what you'll have? Well, there's a no show web, and click the button, and you will see this is just top and bottom L4, no show web. So this is a total I mean 6 sectors, and show web is gone. Right, show web is gone. So I don't want to delete this one, but just I want you to show you the function of how to generate a web. Of course, you can have another web, and this can be easily done. And another important point is that these are scaling factors, and you want to change the Y scale and Z scale, initial and final. Final, I would say you want to change it to a very, say, to the 40%, and Y scale, you want 40%. And this one, I just want to demonstrate initial angle, final angle. You start to 0, and then I will show you dramatic variations. Okay, let's play with it. 180, and then this is just a scaling. And it's important to okay, this is very important. When you generate these sections, and we want to save a different database from 1 to 10 database. So this will scale them. We have a rotations, and all of them will be saved there will be 10 divisions and database. And let's click that. 10 database. You see, save section DB, 10 divisions. So important to know that all these procedures is nothing but generating L4. As you can see that this is 1, and this is a rotated, right? Well, it is a very weird shape, but this So this one, actually, this is all I like to cover today. So this is the it's almost done, and then I will do a little more about. Actually, you don't need to generate the angle of rotation, so I will change it back to 0. And if you click, I'm sure these sections. Okay, as you can see that this section has a uniform, no rotation, but scale. As you can see that you have a scale, and this is how you generate all these airfoil, and you can see the laminate and so on. One thing, and then you go to main, and you can generate geometry as you used to. But very importantly, I'm sorry, not this one. When you generate this section, and now there's another last step, which is to generate geometry. This is the length, same as before, and this is the element. Now this is per element. Now here we generate. This is very important. Okay, this is very important step. Here we have a section dB, which here 1, 2, 3, 4, 5, 6, 7, and 9, 10 were generated. Okay, these 10 sections were generated, and then in the laminate, in laminate, we want to assign a each element as a each section database. To do so, we need to enter -1. Okay, this is a section number. Okay, this is section number, and used to be just number 1, but right now we have 10 sections, and we want to assign and 1 to 10. So if, as you can see, if negative, automatically generate the section number for each element to the number of divisions. So be sure to use the -1 and to have it, to have a different a section. And then you go to a main, and then if you double check this geometry, now you can see that all the element has a 1, 2, 3, 4, 5, 6, 9, and 10 a different section dB for each element. Okay, that's the one thing you need to double check. And the load is very similar to you already know how to enter boundary condition and forces. But now I like to emphasize one thing is the how to enter self-weight. Self-weight is a weight. For example, we have this one, and we have this is the y and z axis. And now let's say z is the one a gravity. If we want to gravity in this way, then this is a z, this is a minus, so this is a -3. So this will be a +3, and this will be a +2, and this will be a -2. So gravity directions you need to enter here. So here you say -3 That means gravity direction will be -3. And then enter this add self-weight. This button will automatically generate this self-weight and in minus z direction. So this will take a couple of minutes to generate all the load due to self-weight. Okay, so actually that is basically what I like to say. And okay, let's wait how it does. If I go to here, see this one, well, number is not quite clear, but this is all I explain in this class. You have you need to define a cross sections. Okay, this is the cross sections, and you can have okay, and you can see there is a number which is a very important number, and scale, I hope you can see well. There is a scale factors, and 50% and 20%, sometimes depending on the your requirement, and save as a 20 database. Okay, there's one you need to be careful. And it didn't show here, but when you generate a geometry, you have to enter -1 to assign all the section dB. Then all the forces are the same. And here is the one example of these deflections. You can enter a certain deflections. And you can it takes a little more time to generate, but basically that's all I like to review again. Okay, it's done. Once this click is done, it brings you to a worksheet called section info. Section info is that we have only 10 elements, 1 to 10. The rest of them, this one actually is a previous one, which you don't have to pay attention. 1 to 10 elements, and each one you have a mass per length, and which you will calculate. As you can see, number is decreasing because of the scaling factor. And also importantly, there is a shear center coordinate and elastic center coordinate. You can, we briefly covered what's the meaning of the shear center, what's the meaning of the elastic center. So understanding shear center is the and also important. And then if you go to a load, worksheet load, and you can see that these new values are automatically calculated, which is about all about self-weight. But at the last term, actually there was a 1. There was a 1, but this self-weight was added here. Okay, so self-weight added here. That's why we have this number. Okay, so this is the how we generate load for the self-weight, and go to a main, and then you can just select, click the this button as usual. Okay, so my point is that that's all I'd like to cover today. And for last homework, which was due yesterday, can be renewed for each group. Okay, using this feature for any wing profile using NACA numbers and so on. And I will soon announce for the tomorrow's class or tomorrow's whatever very soon. But I strongly recommend you, each group, to know how to work together and learn how to use this feature, and hope that you can have a better result. I want to emphasize that, as you can see that if you have the red is the very hot spot, and red is pretty much uniform, unlike the stress concentration at the root. The reason is that this cross section has is reduced gradually, and the moment is gradually decreased. So this is a optimized shape, as you can see that. Okay, so I don't mean to cover everything, all the information you need. This is a fundamental information you need to use this tool to help you to design certain wing profile. Each group needs to study together and work together for better and more complete understanding and how to use it. Okay, again, that is all I would like to cover. And for tomorrow, I will I will announce again, and please pay attention to my announcement. 다시 얘기하지만 오늘 수업 여기까지 하고요. 그 다음에 어저께까지 제출했던 이 홈워크를 다시 한번 이걸로 할 수 있는 기회를 줄 겁니다. 그래서 오늘 한 걸 잘 익히고 내일 수업 전에 다시 한번 제가 어나운스를 할 거예요. 그래서 각 그룹은 이 방법을 다시 한번 열심히 시도를 하도록 하세요. 오케이? 자, 내일 수업 다시 어나운스 할게요. 오케이, thank you. Bye. If you have any questions and use a KakaoTalk, you can send me. Okay? Thank you.